Hey everybody, good Monday morning. What a surprise. I'm here, but only in digital form. I didn't plan on being away today. I got a little sick yesterday afternoon and thought I better play it safe with COVID. So I'm staying home today and getting tested just to make sure. So I didn't want to come to school and risk getting anybody else sick. So here I am. Today we're wrapping up chapter 10 and we just have a short lesson left to do. I kind of introduced it on Friday, so it's not going to take long. And then you're going to get a whole bunch of class time to work and review and get ready for your exam tomorrow. Everything in chapter 9 and 10 is fair game. So keep that in mind as we wrap up our polymer lesson today. So in front of me, I have your notes that I have put into PDF, and I'm just going to go through them with you. So we finished off with addition polymers on Friday. So that was an addition reaction where you're taking those double bonds and opening them up. So this C double bond, we're going to turn into a single with our methyl group hanging down here. It's not going to let me write on it. It's just that glitchy already. Well, that's goofy, isn't it? And then the double bond opens up and you have bonding electrons on either side. Same thing with the next one. Double bond opens up and those bonding electrons on each side can form single bonds. So you get this monomer, two monomers forming a polymer on an addition reaction. I'm not going to spend a lot of time on that. We're going to jump down to our second type of polymerization reaction. Oh yeah, first I have to show you this. I think this is where we left off. So you could be asked a question where you need to identify the monomers. So here's our polymer. You have to look for the repeating unit. So it's a little bit common sense here. Let's take a look. 1, 2, 3, 4, 5. So it looks like my repeating unit will be that. Let's just double check it and see if we can get another one of those of the exact same shape. Yes, okay, so I can keep pulling out the repeating units. And if you had to draw one of them, you can leave the bonding electron open on the side. So it's going to be just a line and then a CH2, C, Cl, CH double bonded to a CH2, and then an open bond on the end. So there's our monomer. Okay, if you had to name it, it would be 1, 2, 3, 4. Well, it's got a chlorine and an alkene, so it would be a butene with a chloro 2-chloro-but-2-ene for that monomer. Okay, condensation polymers. This is what I really wanted to get to today. So this is when you take two monomers, link them together, and remove water. Okay, they're also called elimination reactions, and they look very much like an elimination reaction. So it tells us in the notes, try one of these using a diol monomer. A diol monomer, so diols, OH on one end. Let's just make it a simple one. CH3 in the middle, OH. So there is, that's going to be a CH2. So there's a methane diol, and we're going to use another one of these, OH, CH2, OH. Okay, so we've got two monomers that are both diols. How could we link those together to make a polymer from that? So we need to remove a water. So we're going to take a hydroxyl from one and a hydrogen from the other and pull it out. So that will be our H2O. And it won't let me write H2O. And then we join that together. So that's going to look like, this is going to drive me nuts. HOCH2 to an O to a CH2OH. Okay, there's a 2-unit polymer. And if I was going to do a third one, I would just, again, I'd take this OH away. I'd take the H away from the next OH group to make my water and just link it together. So thinking question, how would the solubility in water change as the polymer forms from the diol monomers. So solubility of this, we've lost two OH groups and replaced it with a C to an O to a C bond. So which one has less solubility in water? Absolutely that C to the O to the C bond. It's going to be far less soluble in water than two hydroxyl groups. So solubility goes down in the polymer compared to the monomers. Polyesters are made using esterification reactions with a carboxylic acid and an alcohol. But they have a C double bond OH on both ends or OH on both ends of the molecule. So here's an example of a polyester reaction, C double bond O, OH. And we'll go super simple again, C double bond O, OH. So there's a dioic acid, propane 1,3-dioic acid. And we're going to put another one here. Double bond O, OH, double bond O, OH. Okay, so this is going to be like an esterification reaction. Well, it is. This time we're using carboxylic acids only, and we're going to remove a water. So the OH from one and the H from the other comes out. And we get an ester linkage because underneath that we're going to get, so C double bond O, OH to the C double bond O to the O, C double bond O, C double bond O, OH. Okay, so here's our ester bond, C double bond O to the O, and we've removed the water. Now we could have also done this if it was just an alcohol. So I'm going to put another alcohol here. OH, C, OH. So we'll put a diol. Same thing again, we can remove the hydroxyl from there and the hydrogen from there. So the carboxylic acid loses its hydroxyl, the alcohol loses its hydrogen to make our water, and we get another ester bond. This becomes a polyester because it has many ester bonds. Polyester, and these can be made with carboxylic acids or alcohols or a combination. So one end could be C double bond O, OH, and the other end could be an alcohol. It doesn't matter as long as we have OH groups on both ends of the molecule, you can link them together and remove a water each time. Okay, so the last thing we're going to do is some sort of look at some examples in nature. So in nature, Mother Nature builds lipids, proteins, and carboxylic acids, carbohydrates. We synthesize those in the lab, and an example of a lipid is a polyester, and it's not going to let me write on there. No, so a synthetic example to fill in your notes for a lipid would be a polyester. A synthetic example in the lab of copying proteins is nylon. So polyester, you might be familiar with. It's a very popular fabric from the 70s, polyester suits and pants and shirts. Nylons from the 60s, 70s, 80s, 90s, even today, lots of you wear nylons. It's also used in pantyhose, parachute pants. I think I saw Kamaya the other day wearing a fancy pair of nylon parachute pants. And carbohydrates, synthetic version of carbohydrates. So Mother Nature makes carbohydrates. In the lab, we make something called spandex, or when I wear it, it's called mandex, but same thing, stretchy synthetic fibers. Okay, so we're going to look at this example of a lipid or a fat from Mother Nature. So there are lots of living organisms that can take glycerol, which is, if you had to name that, any idea what that thing would be named? 3 carbons with 3 alcohols. So it's a triol, propane 1,2,3 triol. So glycerol or propane 1,2,3 triol can be linked up with 3 carboxylic acids. So we're removing 3 waters from this, and we're going to make 3 ester bonds. So this is called a triester. Okay, a triester. And it says down here, label the monomer. Okay, so the monomers on this are a little tricky. Your monomer is going to be a fatty acid right there. 1, 2, 3 monomers. Your polymer is going to be this whole thing joined together, and I'll show you the ester linkage. So it's going to look like this. And I'm not going to label all the hydrogens. So a C to an O to a C double bond O dot dot dot, O to a C double bond O dot dot dot, to an O to a, uh-oh, that's going to be behind me. Can I move that? Sure I can. Park it up there. C double bond O dot dot dot. Okay, so the monomers I've circled. The polymer is the whole thing. And the ester linkage is each of these. Here's an ester linkage, here's an ester linkage, and here. So this would be 3 esters or a triester. When you put these into great big long chains, you get your polyesters, which is what we do synthetically in the lab to make polyester. Okay, another example in nature is proteins. So you guys are made of proteins using amino acids. And the term amino acid, all our biology people, Brooklyn, Bryn and company, Jaden, I think you took AP Bio too. So an amino acid is made up of an amine group and a carboxylic acid. So one end of the molecule is going to have NHH bonded to some type of a carbon. So that's our amine. The other end of the molecule is going to be a carboxylic acid. So amino acids have this basic pattern, an amine and a carboxylic acid, put them together and it becomes an amino acid. So that's in nature. And as it says down below here, oh, maybe it doesn't, but I'll tell you anyway. In nature, there are, I don't have it. Okay. In nature, there are 20 amino acids. Think of it as 20 letters of the alphabet. Those 20 amino acids can be linked in any pattern to make proteins, and proteins are chains or polymers of amino acid monomers, and they can be hundreds to thousands of amino acids long, and they're the building block of life. You are made of protein. If I was the witch in Hansel and Gretel and I decided to stick you in the oven, capture you with candy, stick you in the oven, and then turn you on low for about 2 days and dry you out, pretty much everything that was left there, the 28 pounds of you, would be amino acids and protein. Because remember, you're mostly water. After the water's gone, you are protein. That's the building blocks, and that's all carbon-based molecules. So amino acids. Man, am I just jumping around today. It's late Sunday night, and I'm a little tired. So here's our synthetic example. So for a synthetic example, we're taking a diamine. So instead of an amino acid, it's got an amine group on each side, and combining it with a carboxylic acid, a dioic acid, okay, which has carboxylic acid groups on both sides. So it's a little different. Instead of having an amine and a carboxylic acid on one unit, we've got a diamine and a dioic acid. So this is done in the lab, and this is how nylon is made. And it is a polymer, a polyamide with many repeating amide units. Interesting thing about nylon, so it was developed, I think the original version was like nylon 66. So the guy that developed this was Wallace Carruthers. He was working for DuPont in the, I'm going to say the 30s. My memory fails me, 20s or 30s. He developed this in the lab and then was used in the military. Nylon was used in parachutes. Nylon was used for pantyhose later on. It has all kinds of great uses. So super, super useful synthetic compound. Oh, and we've got some other uses down here for polyesters. Clothing, home furnishing, bed sheets, spreads, pillows, furniture, carpet, curtains, Dacron, synthetic down, fiber, and sleeping bags from polyesters. Okay, the last one we're going to look at. So in nature, Mother Nature makes carbohydrates. In the lab, we copy and make synthetic cellulose, which is a major component of spandex sportwear for all of you cyclists, volleyballers, Gym, people like to work out in the gym and wear their spandex. Well, you can thank Mother Nature coming up with the blueprint with carbohydrates. So an example of this in nature, those of you that took, I think, I'm not sure if this is taught in Science 10 Advanced anymore, but for sure AP Bio, you can build carbohydrate polymers using glucose as the monomer. And if you take glucose and you link the glucose monomers together with an alpha linkage, the polymer becomes what? Pause, starch, right? And there's different types of starch like pectin, amylopectin, so different branching patterns. But this is something that you can digest. We can eat starch and get glucose from it. The second polymer is a beta linkage, and this is a little different. And we don't have the enzyme to break down the beta linkage. And this one is found in wood or cellulose. And there are a few animals that can eat wood and get at the glucose, digest and break off those monomers. Beavers and deer, the ungulate family can do that. We cannot. So for us, if we eat wood, and you do eat some cellulose, it's in plant, fibrous plant stuff, that just goes through your digestive system as bulk, roughage, and speeds things along to give you a fast-moving digestive system, which is good. You don't want stuff sitting in your colon for days and days. You want things to move, and cellulose does that for you. Oh, I'm all over the board today. Okay, so that is it for polymers, your lesson today. So you filled those pages in your study guide. Now, what to do for the rest of the class? Okay, I am missing the worksheet that I usually give you guys. Oh, I know, it's in your study guide. At least I hope it is. There's a worksheet in there on polymers, 1 page. And you really should do that. I've put the answers on my Google Classroom. The second and even more important thing for you to work on is that Chapter 10 review, which I gave you guys on Friday from your study guide. And the Chapter 10 review, I don't have it in front of me, but I gave you those page numbers. It's like, I can't even remember to guess. That's what your unit exam is going to be similar to. You've looked over your reactions quiz that I set out on your desk. And so you saw if you lost marks, where you lost them, and how you're going to make sure you don't lose them next time. Going through that 7-page review in the study guide shows you some more reactions where you're going forwards, backwards, filling in the blanks. That's a big part of your exam, is being able to do that. So everything back to Chapter 9 is fair game, which is why I've also included in your study guide the answers to the Chapter 10 review from your textbook. So if you want to do the unit review from your textbook, you have all of the answers to the Chapter 10 review. There's multiple choice, numeric response, and some written questions in there that you can take a look at and practice. Okay, use your class time wisely, please. You've got lots of stuff that you can do to be successful on that exam tomorrow. I'd love to see you guys finish organic chemistry on a strong note. And some of you I know are flirting with the big hun, and I'd love to see some of you finish this unit with close to 100%. It's possible. All of you can pull your mark up on the exam tomorrow if you put the time in today and do some review tonight and go back over previous stuff. Okay. Sorry I can't be there today. Hopefully I'll be back tomorrow. And take care, everybody. Use your time wisely. Okay. Bye.